disclaimer, I just want to make sure everyone's aware. So I am by no means a battery expert. My background is I'm a vehicle guy. I've been a vehicle engineering guy my entire career. I've spent years at Ford launching electric vehicles, hybrids, and so on. And my role in Capgemini is actually around transformation. So we in today are in the forefront of how do we leverage AI in engineering, right? This is a conversation that's happening quite often. And we push this conversation internally and externally. Clients ask us, hey, how are you guys leveraging AI in engineering? At the same time, we are also pitching to clients on how to transform from current traditional methods of engineering to leveraging AI. Having said that, maybe if I can get a show of hands on how many of you, or maybe on the chat, just indicate what's your level of battery expertise? Are you a deep domain battery person, or are you a vehicle generalist? And the reason I ask is in the last 5, 10 years since the shift towards batteries have happened, almost every battery engineer I've met was either a fuel systems engineer or an exhaust systems engineer that decided to rebrand themselves because they knew that, hey, autos are shifting away from gasoline vehicles to electric vehicles, right? And now they're scrambling going back to their old jobs. But okay, so I saw one is a beginner. Anybody else want to put on the chat? High, medium, low, or beginner, expert, whatever you feel like would be the appropriate, uh, you know, self-assessment. Okay, medium, beginner. Okay, we've got 13 participants, so I should at least have 11 responses. Experts in material. Okay, design for cells and new to pack design. Okay, good, good. Okay, so my hope is that this is a conversation, it's a dialogue, it's a discussion. Your experiences is the content of this presentation. So let me start off by introducing something that's actually happening today in the industry. So FastBat is an initiative in Europe where the industry consortium with universities have pulled together public funds to come up with a tool chain, a methodology or a process for fast battery customization. I mean, there's a recognition in the industry that, hey, the Western countries are way behind. It's taking us too long. There's a lot of repeat engagement and repeat investments in battery engineering. Could we optimize it? Could we pool our resources together? So this forum, you can see it's on public domain. It's an initiative to leverage AI and bring a tool set and an ecosystem together to focus on improving battery development. So this was recently announced. Capgemini, who I'm part of, is very much involved in this. And again, essentially at a high level, it's about how do I use AI to optimize cost of developing an industrialization of a battery pack. It does go into cells and so on, but for the purposes of our conversation, this is focused on the pack. And some of the material you're seeing here is related to that initiative. Okay, so AI augmented battery pack design optimization sounds like fairly complicated, but in reality, it's the fundamentals. It's the same typical domains. You typically are looking at cell format and configuration. Every time I go to a client and we're talking about battery packs, it's always these basic things. Hey, what's the cell format? What's the configuration we're using? What type? Cylindrical versus pouch and so on. What is the physical layout in the vehicle? Is it cell to pack? Is it module to pack, right? Typical discussions on thermal management. Is it liquid cooled, air cooled? Is it mounted internally or externally for cooling purposes? And then discussions around safety. But more importantly, the questions that are coming up now are, how is AI being used? And most of you know today, when you go into designing a battery pack, often you already are anchored by a surrogate design, or you're anchored by some commercial agreement made by procurement saying, we're going to use this particular pack or this particular chemistry. So this is typically how the conversation starts when it comes to engineering, regardless of AI. But the last section is where we'll start spending more time in this conversation. But let me start off with this. Um, how many design variants does your team typically evaluate before a pack design is frozen? If you could put on the chat, if you've been involved in any pack design, what do you think are the number of iterations or variants your team is looking at? Okay, fewer than 10. That's one blend. Okay. Any other responses? None? Besides Glenn. Okay. Um, let me see. Any other comments? You can also speak, by the way. You don't have to be on chat. If you prefer to talk, you can. Okay. So in the industry, it's anywhere between 10 to 50. So less than 10. But if it's a new program, the number of design variants they typically evaluate are somewhere between 10 to 50. Where do you think most of the time is spent in the pack design? What's the biggest constraint that you guys are seeing in this space? Any feedback? I see Egon,
Requirements
you're a
management.
simulation specialist. Maybe what's your view on where is much of your time spent?
The requirements management.
Okay. That's and then this varies from company to company too, by the way. But yeah, it's okay. Requirements management. Anybody else? All right, I'll prompt the conversation. I've also in the auto industry, it's anywhere between A and B. So a lot of CAD rebuild because some change often drives a rebuild of the CAD data. And that's why you'll see some tools out there in the field now that are helping with recreating of CAD data. But yes, requirements management is a big part of it, but that cascades into typically CAD or thermal simulation. So it's mainly these three, but I would say for auto, it's generally in the CAD and then thermal simulation. Um, has your team shipped a design that looked good in simulation, but had thermal and quality issues in production? I know some may not want to reveal that to be that secret, but any experience with something like that?
Yeah, B.
B, that's right. Yeah, yeah.
Reality sucks.
Reality sucks. Well, and you can see, I mean, the Bolt recall was a big one, but that was not thermal. It was more quality issues that led to thermal issues, right? Generally in
But
battery,
it's always the small things. It's always the small things that
it's
get you.
always the small things. That's right. That's right. So this is typically what we're seeing. And now I'll just kind of frame the conversation. And I'm going to call out names if people don't speak. Okay. So just be aware since it's a small group. So typically the conversation starts like this. Hey, we're looking for a pack for this particular product. And the conversation starts with, hey, this is our kilowatt hour rated. We want this much kilowatt hour, and this is a kilowatt target. That's typically how it starts at a very high level. And then it starts with, what's my energy, what's my power rating, and what is my physical envelope that I can package this particular pack into. Am I missing any big ones that you guys can think of, or are these sort of what you're hearing when you think of battery pack engineering? Jerry, any thoughts from your end? Man, you guys are quiet, awfully quiet. Okay. Anybody else wants to?
Yeah, sometimes communication, if it is very important, if the battery is going into an existing system and it has to support that, then they would say it in advance. If it is brand new system development, then that's not inherently bought at the first conversation.
True, true, exactly. So package envelope, maybe it's already constrained by where it's located. Um, and that is an important one because sometimes it could be even like I was in a recent conversation where the OEM was asking us for taking the exact same configuration, same pack, but they wanted to mount it externally to the vehicle versus internal to the vehicle. And I had another client where it was exactly opposite. They wanted to go from external to internal because they wanted to take out costs from the pack, right? So these three inputs largely drive the decisions on what cell format, what's the topology, what's the thermal architecture, structural integration, and BMS, right? So these are one change list can rip through the entire architecture of the pack. Um, Often we also see that when they have a range target that they're trying to meet, or a capacity target because of competition, that change can also drive significant impact to the entire work stream. So just moving on, right? So traditional workflow, and again, this is very typical. An engineer will fix the cell format from experience. Most often, it's actually a commercial conversation that, hey, we already have a commercial relationship with these three cell providers. This is a cell format that I'm constrained by. Their simulation methodology is very sequential. You do CAD and you do thermal and you do structural. And then this goes into a loop. And again, if somebody has a different experience or different view, feel free to share because I think this is a very uh, maturing, area, meaning there's more and more automation happening in here. Typically, like we said earlier, 5 to 20. I think somebody said 10, and then what I said was somewhere between 10 to 50. But that's typically what you see happening. It takes months to reach design freeze, sometimes 6 to 8 months just to do a freeze on the overall layout and architecture. And I can tell you from my own experience that every time we, yeah, 8 months, 9 months, or even getting close to launch, people have moved on, the team is left, or attrition, and we don't know who actually made these decisions on how we got to where we are. Knowledge base is locked in with the expert. And then comes the amazing manufacturing domain, right? Where a lot of the variation, the tolerances are so tight that it's very difficult to meet the high volume manufacturing, production speed. So what's different when you start bringing AI is we are asking clients to be unconstrained in the cell format. And this is something that you can push back in your organization saying, guys, before you go and pick the cell format, we have to do some design of experiments. So what if simulations can be done in parallel? How do I leverage a larger sets of data versus just picking a big constraint to 5 to 20? And how can I move this process fast so I can repeat this exercise if needed, fast fail and repeat it versus going through 8, 9 months to get to design freeze? And how do I retain this knowledge base? This is the questions that we're seeing. And if you're not doing this in your existing organization, it's something to start asking. And we are seeing this um, very, very much in the industry right now. There's a lot of ask from clients to help them in this transition. So moving on, where is the time spent today? I mean, we are seeing a lot of time spent in CAD. Every design change drives a geometry update, and then you have to rerun simulation. Again, there's not an unlimited compute available, and you have to end up sharing that resources. Um, Typically, the team that's doing thermal simulations, not the same team doing structural. Again, if I'm very open to hearing different views, but we've seen more of a sequential handoff that happens in organizations. Um, some design constraint is violated, and you end up having to restart. And one example was in a client where there was a commercial issue that they had to change the supplier. That spun off an entire year-long delay to the program. Very, very expensive. And then you can see requirements management here. This requirements management could be both at a vehicle level and at the pack level. Very interesting. In some of the requirements from engineering was not cascaded to manufacturing. For example, the amount of time for curing of certain material in process before as you're building the pack, for electrical isolation, for dielectric properties. If you don't have those requirements cascaded, manufacturing will make the mistake of sequencing things differently. And then again, like we talked about, knowledge transfer and attrition, very common issues that we have today in the field. So what does AI battery pack design methodology look like? Essentially, what we're talking about is leveraging parametric CAD, and in some instances, even no parametric CAD, using platforms like Cinera. I'm sure some of you are already using them out there. They can create the geometry from scratch, from using some sort of a chat window format where you indicate to the LLM and that, hey, you're looking to build this type of pack, and it creates the CAD geometry. But linking parametric CAD to automating simulation is really what it drives down to, triaging the selection criteria on what is the most optimum parameters for your particular pack. Let me just go to the next slide here. So you can see in this example, based on, again, you're given here in this case, you're given a kilowatt rating, you're given a kilowatt hour rating requirement, you're given a voltage, and then often your cell choice is already made. You've been told by the particular, entity that's commercial or it could be even surrogate cell that you have to use for scale. Just using different cells to achieve the same performance criteria, you end up having to make different trade-offs. And this is just an example of, say, a large cylindrical cell, still 112 cells, but because of the way you're configuring it, it'll have 18 strings. Total number of cells is 2,000, and it comes out to about 380 kilograms to the pack. Of course, this is just a cell with modules, but not the cooling and other aspects of that. And then you're looking at how you would be packaging something like this. So same power ratings, different cell formats can yield different combinations, different pros and cons as well that you have to deal with. But this is just an example to illustrate the point. Now, in the math that you're putting together for building a pack, these are the inputs you typically put in, and you have, this is again for those who are more technically centered around the pack. You're looking at, these are the different equations you're looking at, but then here are the constraints you have to satisfy. So these are all the inputs that go into something related to how you would optimize it. And I'll just go on to the next line here. Now, I want to park here for a little bit and get some feedback from you. So in the cell topology bucket and thermal management bucket and structural packaging, I broadly laid out the different variables you have to look at. So under cell and topology, you've got about 8 variables. And if I assume 5 different settings for each of these, you're looking at 390,000 combinations. This is just in one domain. Now you start applying the same across the 3 domains. The number of permutations and combinations you can build are very large. You're looking at million plus. How do you leverage AI to triage something like this? Let me just go to the next slide and we'll park here. So the methodology that you leverage to narrow down from millions of combinations to 5 to 10 is really, rather than starting off with 5 to 10 being and you're anchored up front, this is really what the power of leveraging AI is. The first phase of filtering is physics-based, right? So you have certain mathematical calculations you can make that simply can narrow down based on, say, for example, what is the nominal voltage you have to hit. You can rule out quite a few combinations by just applying this constraint. And just going through a few of these examples here, you can cut down from 10 million to 50,000. And this is being done through leveraging AI. So the first sanity check of applying physical and hard constraints, you can get down to 50,000. Then you start applying using trained machine language models. Platforms like secondmind.ai are leveraged to use surrogate models to filter from 50,000 to say 500 to 2,000 parameters to work with. So this is another filtering. And then you start going into further tunables, what I call variables that are sensitive to driving huge impact to performance. For example, channel width can impact 58% of the delta in temperature variance. So these are more sensitive parameters that you want to work with. And then those that have low impact, for example, plate thickness only influences 5% of the delta T. So maybe it's something you can lock down upfront because its impact is low. By applying this very simple and fixing the low influence variables, you can bring that down to from 2,000 to 50 to 200 candidates. And then running further DOAs on sampling, where you can see a lot of this is again on predictive confidence, further improves that from 200 to say 20 to 40. And you want to live, when you reach this point in your data sets, this is where you really want to have the engineering input coming from applying engineering judgment, and I'll walk you guys through this. So this is typically how you see AI driving, starting off with millions of combinations to coming down to 5 to 10. And like we all said earlier when we started the conversation, most organizations start with 5 to 10 because often they have a surrogate design or they're constrained from what they're procuring. Does this resonate with any of you, or have you had similar experience with this kind of a triage methodology in battery development or pack development? Any thoughts, any comments on this? Or any areas that you guys have been using that you found to be more effective? No comments? Okay. We'll keep, I'm looking at the chat window as well at the same time. Okay, no responses. All right, just moving on. So, like I'd mentioned, the rather than starting from 5 to 10, triaging down from a million plus using AI gives you the best bang for your buck. And we're still talking about maintaining timing and maintaining and improving the timelines. Thermal management, often like I mentioned, in the traditional flow, it's typically structural work done, and then you do packaging, then you do structural, and then you start looking at thermal. Or depends on the OEM, they might be looking at packaging, thermal, and then going to structural. In the format that leveraging AI, you can actually do these as a co-design in parallel versus it being an afterthought. Just moving further. So this is what I would consider when you get to that 5 to 10 different combinations to work with. This is where you apply the Pareto model. So for example, the way to read this chart, if you're looking at reducing the pack weight from say 100 kilograms to say 70, you have to be able to buy and accept the temperature increase by 3 degrees. Or in other words, if you want to lower the peak temperature by 3 degrees, you have to make a trade-off in terms of temperature. So each of these data points is an optimized DOE that is supporting one or few other optimized parameters. And you have to look at, if I was an engineer or a program looking at what are the main criterias, if I was looking at range being my most important criteria, and then I have to look at lowering my mass. So if I'm lowering my mass, then I have to, accept the higher temperature impact. So this is how you would start looking at applying more filters related to the application of the overall product. It's not now related to the pack itself. It's more around the attributes of the vehicle now. If I'm looking at safety first, then I'm certainly looking at optimizing my peak temperature. If I'm looking at cost as a criteria, I need to minimize my cell count. Which of these would result in a lower cell count is what I would be looking at. So this is how you would look at. This is where the engineering judgment really comes into play. Just along the same lines, using the simulation tools to optimize to mass and stiffness and crash integrity, along with the parallel simulation of thermal, as we talked about earlier. I'll just keep moving on here. Same thing with optimizing first-time throughput. This is an interesting one. We found that when you design for quality and you start looking at how to optimize using AI for FTT, in some of the pack designs, we've been able to see 15 to 28% throughput improvement in FTT just by picking the right optimized combinations of the parameters. And that alone translates on 1 percentage point translates to 20 million in warranty spent or warranty saved. So in my mind, if this is designed into the process, you can achieve anywhere from 15 to 28% throughput from one example that we leveraged. Overall, what we expect to see with leveraging AI in your battery pack design is being able to evaluate 10,000 plus variants and combinations and narrow it down to the 5 to 10 that we talked about. And then you're looking at getting to that Pareto model in 1 to 2 weeks versus typical engineering taking anywhere from 6 to 18 months. Overall program compression is 3 to 6 months. We're actually seeing that in the field. Optimizing the pack weight by 8 to 15%, reducing physical testing. And this is huge in terms of both cost and timing by 60 to 70%. And then more importantly, improving the first-time throughput and quality. Shifting left in the inspection process versus getting things to end of line is important in leveraging AI. And lastly, just to kind of wrap up, right, is it's not about what's the best chemistry. Really, it comes down to how do I optimize the variables that I know in pack development using leveraging AI. So it's not about, the best architecture is not, who's the best engineer, but really is pushing the boundaries of using AI to find that one combination that we haven't explored yet. Really, that's what it comes down to. So let me go back to this. Are you guys seeing something like this in your daily work, or maybe this crowd hasn't been too chatty, but I'm keen to see and hear what you guys think about. Are these results what you're seeing in your field, in your company?
I believe it's reasonable. I would say what you're showing is, I would say, compared with my experience, what we are doing in Born Electric, we setting up the exchangeable batteries. So I would say, and another dimension is, I would say, not full battery pack, but also size of each section.
Module,
and the
okay.
and the connectivity, because I would say a socket is always, if you exchange part of the batteries, is always the question mark, because there is no dialogue solution when you can, depending of course of current and voltage, there is not so many possibilities, so it really limits us with some designs. But as you say, all this calculation we are doing in the Excel sheets, so if it can be supported by AI, it's really a good idea, maybe.
Yeah, and just to follow through on that, and you're right. It's like when you look at, I spent a lot of time in engine development, right, my career. And if you look at just designing a cylinder and a piston combination and the amount of number of DOE iterations you can run, right?
Yeah.
We in the auto industry know this. We've been doing it for a long time. So we've been using simulation. And to your point, it's been largely moving data back and forth, leveraging Excel files. A lot of that optimization is already now happening in leveraging AI and LLMs. And again, Second Mind is a tool out there that Mazda has been using to optimize their engine development and calibration. We're seeing more and more of that coming into battery development, and that was really what I was trying to impress on this audience is if you're not using AI tools in battery development, you're missing out. It's a huge cost to your vehicle or to whatever system you're using it. Getting this kind of throughput and productivity, leveraging AI, is very important. The Chinese are using it for sure. I've spent a lot of time with them on this, and it is an area that they've mastered. So certainly, yeah, thanks for your feedback. If I heard you correctly, you're saying you're using it for module development. Is that my understanding correctly?
Yeah.
Okay.
Module development for exchangeable batteries. So we have small modules like 1 to kV hours, and then we are setting up in the bigger battery pack for mostly for vehicles, but light vehicles. So you can, instead of charging the vehicle, you can exchange the battery as a system. Like in DIY tools, for example, where you have packs, we have this concept with our BMS of exchangeable batteries. But market goes in another direction. Only NIO has something outside platform to exchange the models, but others are, binding the battery with the vehicle, which I believe is not an overall good idea, but it is what it is.
Yeah, no, I agree. Any other experiences? Again, like I said, this session was not to teach you about battery engineering, but was more around this notion that, leveraging these tool sets now in battery development is critical. We've been using it. We've been using similar tools in other aspects of engineering, but not so much in battery pack. And I think it's why I think it's an important conversation to have. Anybody else? Any tools you guys out there are using that we should be aware of that others might benefit from hearing? I mentioned like Synera as an example. We partnered with them, and Synera is an orchestration platform that allows you to move. You can create workflows and rules to move from CAD to CAE and to simulation, and to drive a lot of that automation between different tool sets. And like I mentioned, Second Mind is someone that has been developing a lot of surrogate models that you can use so you can reduce the number of simulations you need to run, right? Any other tools out there that you guys can recommend? Okay. I think if I remember correctly, was Igor. I think you said Igor. You're a simulation specialist. What tools are you using? No response. Bit of a shy crowd, unless you guys are. Some of you might be overseas in different countries. So I don't know where you're calling from. It might be late. Yeah.
Yeah, I guess at least in our end here in Germany, it's a bit late. Yeah. That's why the mind is stopping.
Maybe that's the result. I'm from Poland, so the same time as in Germany, but like 7 afternoon.
Yeah. No, I see some folks from could be Asia as well, but I could be wrong. They could be right here in Detroit, Michigan. I don't see
Yeah,
any.
but I mean, the concept itself of really accelerating the process, whenever you can do it, especially in the R&D part, is really appreciated because you drag your development costs down, and at the end, the cool question is always how much you can bring through non-costly solutions, non-testing, and simulation, which can really guarantee the real performance of the product on ground. This is always our problems as scientists and engineers.
Yeah.
In any problem which we try to solve. And for batteries, it's a bit complex.
Yeah.
This is the issue.
It is. And the notion that you can also run unlimited simulation using AI can be expensive too, right? And so because of now the token costs are going up in many companies, the CTO or the CFO or the CIO is willing to spend the money, but wants to know what am I getting for that token I'm spending, right, on using AI. So it is certainly important to um, triage this to rather than starting from like the 5 to 10, but triaging it and then repeating that exercise selectively and building
Yeah.
the knowledge base. Yeah.
But I can add here just one maybe last point from my side. It's not only the cost, it's will really AI bring and add value? Because when we discuss about safety, it's a critical issue. And to do this over battery management system, still the expertise in this field say that problem of AI is always, I did develop AI models myself, and you never understand the correlation. You never understand how it works from inside. So you will never be able to tune parameters if you see something wrong. And this is the main issue. That's why my point of view is always that we will use AI, especially when safety critical issues for batteries, as a very sophisticated calculator, not as a solution.
Yeah.
So we'll use like accelerating physics-based models, calculations through AI. This is what I see realistic. But using purely AI instead of physics-based models, I don't see this even acceptable or scientifically correct.
Yeah.
So this is as well an approach which we need to take into account when we discuss really using AI in terms of as a solution provider, especially for managing our systems and especially for the battery itself.
Yeah, that's a good point. Good point. Glenn, are you in Hong Kong? Is that what you said on your chat?
Yeah, that's correct. I'm Hong Kong based.
Okay. And Glenn, I mean, again, I spend time with the Chinese partners, but I'm largely dealing with the big ones like the CATLs and so on. What are you seeing in the smaller players? Are they or the OEMs particularly? Is that something you have visibility to in where you're out there in the
Not really, because I'm more on the business development side, so I touch everything. So I have a good amount of battery knowledge. A lot of it's come from being punched in the face with it starting on EVs, going into, say, regular consumer electronics, and now going into, say, power applications with the data centers. So just how it keeps evolving. I mean, the tools are changing, but there is all at the end of the day is still the liability aspect and repeatability. Because I see a lot of the Chinese, yeah, they're using the AI, but then also the Chinese can allow a lot more higher amount of risk in terms of failure.
That's
I
true.
mean,
Yeah, yeah. The
you got the
threshold is
classic
things like,
case
yeah,
with BYD. I mean, if you saw BYD back in the early 2000s or even the 2010s, it's like every day here we had a story of, oh, another taxi caught on fire, another BYD hybrid bus caught on fire.
right, right.
If that was happening, say, in Europe or the US, BYD would be bankrupt.
I agree.
So when you have the Shenzhen government says, yeah, no big deal, fire, move on, get on
Right.
board, walk.
Yeah, it's
Yeah, yeah.
true. That's
That
true.
is a very interesting point. You are totally correct. This work, but maybe I can comment here as well. But because the Chinese development cycle will get slower, more costly, because they are getting exposed to the wallet system.
The regulations and whatnot. Yeah,
There is no way to avoid this. But this is a normal cycle. What we see here, what we have seen in China along the last 15 years is basically two things. It's a failure of what Hydro-Quebec did do for LFP, not really forcing their patents in China. This is 30 years ago. So that's why we
Hmm.
see a lot of development of LFP in China, and this will not happen again. Plus, that, um, as mentioned here, allowing risk appetite to be very high locally. But this is acceptable locally. Once you get exposed to the world system, once you get exposed to the EU, once you get exposed to the big markets, to the influensive parties, it's just one generation, and then Chinese costs will go up. People will need to work only 8 to 10 hours per day, and as well the risk appetite will go down because standards. So this will work only in developing um, countries, like acquiring a lot of new markets in Africa, for example, in the Middle East. I see this in Asia, but it will not. It cannot be sustainable once you get it up.
yeah, yeah. I think we're
Yeah,
almost
look at
out of time, but this is. I think it's good to. All I want to leave this thought with you is in your design development cycle, you have to think about where can I infuse AI. Maybe it's not every area. Maybe it's that maybe it's narrowing down to maybe it's thermal, maybe it's the package envelope, whatever is your organization's appetite. I think to your point, Mohammed, you said the correlation to the physical is so important with PACS that we just don't have that much surrogate data and correlation data to lean on this tool, but it helps you triage it down to that much smaller subset where you can actually go spend that time and money. But well, thank you all for your interest and time and your contribution, and hopefully it's still some time the rest of your evening.
it.
Have a good day.
Thank
All right,
you.
have a good one.
Bye.